Hello, this is Jennifer. Today we will talk about LeetCode 42, trapping rainwater. The question is, given a non-negative integer representing an elevation map where the y of each bar is 1, compute how much water it can trap after raining. Alright, let's dive in and see how this situation plays out. The rain keeps falling, until you can see that it's now at its max capacity for trapping water. So how much water it can trap, how to calculate? To answer those questions, I would like you to rethink our real-life use cases. Number 1, drum gate, also known as the stop gate. These gates are idle for controlling the water levels. This stop gate is typically the highest barrier, ensuring that no matter how the water flows, I'm absolutely certain it will be blocked by this stop gate. So we have a general direction that if we can find the highest barrier, things will be easier. Number 2, wooden bucket theory, also known as short board principle, referring to the shortest board on the bucket determines its capacity. First, we will take a look at the array of input barrier heights to find the highest barrier, as we have a general direction that if we can find the highest barrier, things will be easier. Notice that now, when the index is 0, the height is 0. When index is 1, input height is 1. When index is 2, input height is 0. When index is 3, input height is 2. And so on, and so on, and so on. So we are able to find and record the index of this highest barrier. Why do we need to record the highest barrier? For the range from index I to index peak index, since I recorded on the right side of the highest barrier, I'm totally sure there is a barrier on my right side that's going to help block and trap the water. So it can help us just focus on this range's left side. Let me dive deeper. Now, when point I points to a current barrier in the height of 0, we initialize a variable, the left highest barrier, to 0. If so, no water will be trapped in this position, so our trapped water will be 0 here. When pointer I points to a current barrier height that is higher than the previous leftmost barrier, I updated this leftmost barrier to this one because it will impact the trapping water on its right side. When point I points to a current barrier height that is lower than the leftmost barrier, it indicates that this position is a lowland and can trap water. Why? Because for this specific position, regardless of what its neighboring right bar looks like, we have left highest barrier to block its left side, and we can be 100% certain that we have a right barrier to block its right side. Let's consider an extreme example. If there is no neighboring barrier on its right side until this highest barrier, the water at this specific position can be trapped is still 1 unit, right? Since I cannot see the part that index I hasn't scanned yet, I will temporarily pretend to ignore this rest part. What can I get for the current position? I can trap 1 unit of water. Based on the wooden bucket theory we mentioned, between this leftmost barrier and this highest barrier, the shorter barrier determines its water trapping capacity, which is 1 unit of water. Let's move index I to the next position. If the current barrier is higher than the leftmost barrier, it means that leftmost barrier needs to be updated because it will impact the trapping water on its right side. If the current barrier is lower than the leftmost barrier, it indicates the presence of a lowland, which means that this position can trap water. Since I cannot see the part that index I hasn't scanned yet, I will temporarily pretend to ignore this part. So for this specific position, water equals to leftmost barrier height, which is 2, minus this barrier height, which is 1, so we can trap 1 unit water here. The water amount currently increased by 1 unit. So we will update total water to 2. Let's continue. For this specific position, if current barrier height, which is 0 now, is lower than the leftmost barrier, it indicates the presence of a lowland, which means for here we can trap water. So for this specific position, water equals to leftmost barrier height 2 minus this barrier height 0. We can trap 2 unit water here. So the water amount currently increased by 2 units. So our total water is updated to 4 units. Let's continue. For this specific position, if the current barrier height, which is 1, is lower than the leftmost barrier, which is 2, it indicates the presence of a lowland here, which means here we can trap water. Water equals to leftmost barrier height 2 minus this barrier height 1, so we can trap 1 unit water here. The water amount currently increased by 1 unit. So our total water is updated to 5. So for the left side of highest bar, we can trap 5 units of water in total. We will use the same method to calculate how much water can be trapped on the right side of the highest barrier. Alright, let's go through code together. First, we use a for loop to scan through the given array of barrier heights to find the highest barrier and record its index. Second, we calculate how much water can be trapped on the left side of the highest barrier. Third, we calculate how much water can be trapped on the right side of the highest barrier. Finally, we return the total water added from left side and the right side. Alright, that's all for trapping rainwater today. I hope you liked this video. Thanks for watching. I'll see you next time.